Okay, so we can start
Progress.
about computational thinking. So as I said, computational thinking is not thinking like a computer. If we had a really short definition for computational thinking, we'd say thinking in such a way that you solve problems and you organize the problem so that a computer can be used as a tool to help you solve the problem. You don't have to use a computer to solve the problem, but you're thinking in a way so that a computer could be used to help you solve the problem. Then you're computational thinking. Doesn't mean you're writing computer programs. You could be, is your hand up to ask me a question? Sorry? All right. So as it says there, before computers were used to solve problem, you have to understand what the problem is. Before you can solve any problem using a computer or not, you have to understand what the problem is. Problem solving methods, right? So if you're doing a business course, if you're doing a science course, you would still look at this way. And in fact, in Jeanette Wing's article about computational thinking, she sort of argues that everybody should study computing at university, at least one course, so that they learn computational thinking, even if they're going to be a doctor or a scientist or an accountant, because the technique that you learn can be applied to other things. You don't need a computer to be doing computational thinking. So as it says here, computational thinking allows us to take a complex problem, understand what the problem is, develop possible solutions. We can then present these solutions in a way that a computer or a human or both could be used to solve it. Does that make sense? That's computational thinking. So computational thinking has been thought about quite a bit. There actually is, students ask me first week of this course, is there a textbook? Well, yeah, there kind of is. And there's a textbook that's problem solving with computational thinking. And I think I put the name of it on one of the earlier slides. I think it's written by Beecham. So now I use Scribd or Scribd, SCRIBD, to access that, because, and if you wanted to, you could do the same. And it's like a charge of about $8 a month to do that. But the thing about Scribd is you get lots of books. You don't just get that book. There's lots of other books you can use. And it actually has audio with it. So you can listen to the book as well as reading it. All right, so I told you there was 4 components of computational thinking. During this course, you'll look at each of these individually, like I think spend like a week on each of them. So you should have a fairly good idea of them by the time we sort of finish the course. The idea about decomposition, there's a very small graphic there in the corner, which is supposed to represent what decomposition does. And I hope you can see that. What it is you have a big problem that we're not sure what it is. We break it up into smaller problems. And we keep breaking it up into smaller problems until we get individual problems that are small enough for us to start to solve them. Now, when I first started studying computing 100 years ago, right? We used to call that stepwise refinement. Stepwise refinement, which is to break the problem down into smaller pieces. So it's something we've been doing for a long time. So Jeanette Wing was talking about this since 2006, but people have been doing stepwise refinement and decomposition for a long time. It's the way we always do it. Now, when I say it's the way we always do it, what you'll find in computer systems is you have a big problem, you break it down into smaller problems. Each of those problems then gets implemented as a module. And so you have a program with lots of different modules. You know what I mean by a different module, right? So you can see that if you're not very computer inclined, you can see that in a example of something like a car. A car is a system, and it's a system we have a lot of things that we want to do in the car. And so we have a lot of modules in the car. So you have a module on your brake system so that you have anti-locking brakes so that you don't skid when it gets wet. You have a module for your engine, the timing and the amount of gasoline or diesel that's going to be applied to the engine. That's managed by a computer, different module. Each of those are quite big modules. And there's quite a lot of them. I think we mentioned before when we were talking about computers, the type of computer called embedded computers. If you have a computer that's actually used in a device which does a lot of other things, but it uses the computer for one little part of what it does, we call those embedded computers. And your car has lots of computers in it. And as I said, each of those may be applying to just one single module. And actually, that's, I don't know if you're interested in that, but very hard to buy a car in some places at the moment. I went to buy a car a couple of weeks ago in the United States, and I went to car yards, and there was car yards without any new cars on the lot. And they were not able to supply new cars because the chips that they use for all of those embedded computers were not available, because ships aren't getting out of China, and now ships aren't getting out of China or Taiwan. So I expect this to continue for a little while, right? So if you wanted to buy a car, it would be better if you did it a couple months ago than now, right? So those kind of small chips that are used for those types of things, you can build a car without it. And in fact, I read an article that Iran, 100 kilometers away from here, right? So of course, a bit further away from that if you go to the car building factory. But their way of solving the problem is they just build cars without chips. So they're basically building 1980 technology cars, but that's good, right? It's not going to stop, because cars used to work without computers. All right, so that's decomposition. Abstraction. The idea of abstraction is you have a problem and you see you got lots of information about this problem, so much information, but then you realize that actually a lot of this information isn't helping me solve the problem. What if I just focused on the stuff that actually I need to solve the problem? We could do that by removing a lot of the information, just focusing on the really, really pertinent stuff. We call that abstraction. So abstraction is taking something complex and representing it by something a lot more simple. When you draw a diagram, that says, and you show it to your friend, this is where my house is, you know what I mean? And you draw 2 lines and an arrow there, and you say, okay, there's this villa on the corner there, and it looks like that. It's got a green door, and then mine's beside it. That's abstraction, right? It's not giving a full picture. It's just sort of a little sketch that'll get there, right? When we draw stick figures for people, that's abstraction. We do a lot of abstracting, and of course, we need to do abstracting to do computing properly. So, I think you can follow this around sort of in a clockwise manner. The one on the bottom right, that diagram there, hopefully you're familiar with looking at something like that. That's actually a flow chart, and there's abstraction in that, right? Each of those symbols means something. So the person who's used to flow charts can look at that and automatically it means a lot. So we use flow charts as one way of representing an algorithm. So an algorithm is going to be a step-by-step process which is used to solve the problem. And so we can do that. We can show that with flow charts. We can show it with other means as well. We may have spoken about that in a previous lesson. If not, we'll talk about it in later lessons when we get to that. Pattern recognition. So what happens is we look at what we're doing and we realize, hey, this is kind of like something else that I did before. Maybe I could use that here. And so we use we reuse modules, code reuse, something which is similar. We can or group things together. We do loops, etc. If you see a pattern, then you can simplify what it is that you're trying to do. That is used a lot in computing. And so I hope those things make sense to you. I put that out of order. They should have gone anti-clockwise, it seems. Oh well. Complex problem, decomposition. So as I said, there's the first one there. Break it down into smaller pieces. Then each of those smaller pieces we can approach in a way that we can solve it. Now, one of the things that we can do mentioned there is we could apply pattern recognition, which is that we see that this is a problem similar to one that we did before, or it's a similar, or we got 2 problems that were similar, maybe we can group them. Then we can sort of apply, we can reuse. Abstraction, focusing on only the important stuff, throwing away all the other stuff. And lastly, we do the algorithm. Actually, not lastly, we do the algorithm before we write the computer code, right? The computer code is the last thing we do out of these things. But these things we are applied before we get to the computer code. Now, I'm not too sure, but I do think that there's probably a question in the quizzes that will talk about the order of things. So I don't want you to get mixed up, because I actually did this not in this order, didn't I? I went around clockwise, and it wasn't clockwise. It was down, 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 down. Read the left, then read the right. So do pay attention to this slide if you're studying for your test. that you get the order in the way they want. The most important thing about the order is all of these things have to happen before you actually write the code, right? Before you write the code, you have to do all of these things. Now, yeah, very important point. Computational thinking is not thinking like a computer. It's not writing computer programs even. You know, so I suppose you could say that somebody who's sitting there writing some code, you know what I mean? When I say writing code, somebody might give you an algorithm and say, here's the algorithm, because you're a coder, right? And they give you the algorithm and say, okay, could you please turn this algorithm into code? And so what skill you're applying at that point is your excellent understanding of the syntax and being able to write that code. That's not actually computational thinking. That's something else, right? It's skill in coding, which is different than computational thinking. So you get what I'm saying? So, I mean, there are people that might be working in the computer industry, spending a lot of time every day writing code, but maybe not doing computational thinking. Does that make sense? The ones who are doing computational thinking are the ones that are taking the problem and saying, this is how we would solve that. This is how we would solve. Then we're doing computational thinking. Does that make sense? So, all right. So, programming tells a computer what to do, how to do it. Computational thinking is different because it actually allows you to work out what it is that you have to tell the computer to do. So let's have an example. You agree to meet your friends, going out for social. So you consider how you're going to meet because you're coming from different parts of the city. And so when you do that, you would come up with multiple, possibly, I mean, you know, there's not just one road in the city, there's multiple roads, and you might come up with multiple sort of solutions to that problem. I'm going to meet my friends at Katara. Okay, so I could go to Katara, you know, I could go down there by the university through the place where they have the lagoons. I can't remember the name of that place. I could go that way, or I could go down this way. What's that street? Kafji Street. I could go down to Kafji Street and straight down to the Intercontinental Hotel and do a U-turn and go into Qatar that way. Or, you know, there's other ways that I could go. So which one would I choose? And so maybe I'll choose the fastest. That's one solution. Maybe I'll choose the one where I have less traffic lights. You know, maybe I'll choose the one where I know they don't have as many speed cameras. I mean, you know, we each have a way that we would say this is the optimum solution. And maybe my optimum solution is not the same as yours. But we would typically come up with a couple of them. So that's the thing in computational thinking. We usually come up with more than one solution, or we don't put all the flesh on the bones of that solution. We come up with a concept solution, and then we choose the best one. And then we go and make part of it, do something with it. Planning is like computational thinking, and following the directions is like programming. And so I hope I made that example before like that, right? When we decide which one we're going to do, then after we decided, okay, so I decided I'm going to go to Qatar down Kafji Street. So I'm going to leave here. I'm going to turn left at the intersection, then left again, then straight down, and then do a U-turn. That's how I'm going to get there. And I could just, those are the steps, right? That's my algorithm. Leave the car park. Okay. Just following that, that's not computational thinking, right? I mean, all I do is once I've gone onto the GPS, right? And I've chosen that route, following that, that's not computational thinking. It's just following instructions. Okay, so, but you've been put in charge. So, like I said, you know, some people, they care about that they don't go past any speed cameras. Some people care about the shortest way. Some people have a very fast, low car. They don't want to go over any speed humps. You know, I mean, so they have different things. So, for you to decide which way you want to get there, what's the best way, you might want to ask them some questions. So what kind of questions would you ask them? What kind of questions would you have to ask them so that, this time we're not talking about going to Qatar. We're talking about some social activity. Let's meet. Okay, what should we do? What should we do when we meet? What are you going to ask them so that because they asked you to be put in charge. I hate that. I don't know, maybe you guys like that, but yeah, what I got to decide so that everybody's happy. What chance is that? Like zero, right? So, I mean, you're only going to get to the thing where everybody's not too unhappy that they won't come. So you'll get as good as you could get, right? So what kind of questions would you ask them?
How we can go to that.
Yeah, we'd ask that. Okay, what about transport? Any other things? What exercise do we have, right? Because he's a fitness dude, right? So, yeah, what exercise could we do? Any others? Yeah, you might ask them about eating. You guys want to eat something? If you do, you want fast food or you want to sit down? Do you want to watch a game? Because there's a game on. We could go down to the jet ski launch and we could do that for a bit. I mean, depend on what you want to do, right? So you could ask things like that. Where could we go? Who wants to do what? Oh, that's a good one. Here's a pattern recognition. You see the pattern recognition coming up here? What have we done before that worked? And most people liked it. Only 2 people went home early. So that must have been good. How much money do you want to spend? You know what I mean? Are we going to hire out the cinema for just 3 of us? Or are we going to go and sit in the cinema with everybody else, right? What weather? This question we don't need in Qatar, right? We know what the weather's going to be until November. Then it'll change. Well, that's not true, right? We had rain a couple of weeks ago. That was awesome, wasn't it? How much time you have, right? So is it a 20-minute sort of thing or is it 2 hours? And this is the question that was asked by Ibrahim at the start. Here's another one, right? Here's a computational thinking task. We're looking at the video game. Here we are. We're the player. This is our avatar. And I guess I don't play video games. So for sure, I'm going to say this wrong. See, so you can tell me right if you want. But it looks to me like it would be a good thing to get this key. I guess so, right? Because that would help you get to the exit. So you probably need that key. It looks to me like these sort of skull things, they probably be bad, right? You probably wouldn't want to land on them. Yeah. All right. So then how would you get from here to here? And you have to pick up that, right? So, I mean, you could come up with some steps and maybe you know more about the game. I was looking at this, I was thinking, well, the guy has to sort of like turn sideways and go past this. Or maybe he has to have some kind of weapon that he can neutralize these enemies. Is that how it works? Like you can shoot them or something without touching them? Because otherwise you got a problem, right? So you'd have to go up there and like shoot that one. I guess you could climb up the ladder or else you got, anyways, you could. Now, what do you need to collect? I think you need that key. What do you think? Because this looks like that door is locked. And that's the only way you're going to get out. So it means you're going to have to go there. You're going to have to skip these things, right? Because you fall in those holes, then you just keep climbing, right? So you have to be able to jump. So you notice there that you have to know what you have to collect. You have to know how can you collect it. So yeah, what happens when you come to the key? How do you collect it? It looks like there's only one exit. And what can we do to neutralize our enemies? And hopefully you've got some tool to do that, right? All right, so this is sort of a little word game thing. No, not a word game thing, but you see, and now it's in the right order, it seems. But what these are color coded, and what we're going to try and do is we're going to try and get each of these in the right place, I guess. What happens when I click once? Yeah, that didn't work very well. All right, so let's go back. All right, so what is decomposition? There should be an explanation for it. That sounds fair, right? So we'll check this out when we get back. So here for the explanation, we should have breaking down a complex system into smaller, more manageable parts. What is pattern recognition? It's probably hiding underneath this thing, right? Looking for similarities. Yeah, I'd go with that one, right? So I think we got 2 of them. What is abstraction? Very good, Shaza. It is focusing on the important stuff only. And what is an algorithm? The only one that's left, right? Hey, you know what we just did? We did process of elimination, which is a logical thing. Computational thing? Kind of. One way of solving a problem is to sort of eliminate all of the things that are wrong. And if there's only one thing right, well, it must be that, right? Okay, so meeting up with friends. Which one would be decomposition? I think it might be this one. Options are where to go. And you think so? Options means more than one thing. It's plural. So which? Okay, and then what would be pattern recognition? Yes, that's what I read. What you've previously done would be pattern recognition. What would be abstraction? Sure. Abstraction is making it as simple as possible. Yeah, I think it might be. So, what are we going to use? A cab or our own car? And then, so no, the reason why I said that, Abraham, is because this is step by step. This is a step-by-step solution, which sounds like an algorithm to me. And the last one, creating a computer game. What would be the explanation? Sorry, what would be decomposition? So we're only using these yellow ones now. Decomposition, explanation of how to complete the level. I think it might be this one because this is tricky, but I think it's that one. Why? Because there's multiple ways it's plural, and so pattern recognition would be including similar because we've done it before. There you go. Pattern recognition. We've done it before. Abstraction, making it simple. I think location of the exit. Very good. Where's the exit? And then lastly, explaining step by step how we get there. And so I think that's right. Yeah, there you go. So they've given us their answer, and you can check that yourselves. So it seems to work, and that could be a step-by-step process of computational thinking applied to 3 different problems, which are not using a computer. So you don't need to use a computer to do computational thinking, right? All right, so use word problems, and from the word problems, we may or may not put them into a computer system. I think that's all it's saying. Okay, so here's our example. Customer called the IT manager, expressing a situation they had faced, trying to control the spread of COVID. They were thinking, so how is IT going to help us do that, right? They were thinking about technology that can help. The IT team worked hard, thought about the problem, and they gave us an app, which has a lot of different modules in it. Things like, and I think you must always be in some kind of Bluetooth contactor, right? So, it must be turned on, and it must be Bluetooth. And then every time it meets another phone, which is within range, 2, 3 meters, it exchanges that COVID information, right? And so if you come near to somebody who's got a red, your thing will show that came near to somebody who's got a red. And then they'll come and tell you to come and do a PCR test. Or go and isolate or something. So, that's the idea of it, right? If your phone is turned on, the Bluetooth is on. Did you notice that? The only way to turn it off, I think, is to uninstall the Ethers application. And that's not a great idea, because if you uninstall the Ethers application, then when you go to reinstall it again, they will not, They might sort of say, well, you can just wait a while. We got to check out some things about you before we let you have that digital certification. Meanwhile, you can stay at home. Yeah, so yeah, don't uninstall the Ethers app. You have a problem. You're ready to start analyzing it, coming up with a solution, but not just any solution. One that is specifically formed so the computer can query it. Oh, okay, so what's the deal, right? You begin by looking at the problem. The question dawns on you. Where on earth do I start? Yeah, where do you start in solving a problem? This was given in the very first slide. Maybe we don't remember there, but you need to define, you have to define the problem. You have to look at the problem and sort of say, okay, this is, it just restate it in your own words or whatever. But understand and define the problem. That's the first thing that you must always do. It can be helpful to follow some kind of guide, like instructions for a piece of self-assembly furniture, like IKEA, right? IKEA makes really awesome instructions for assembling furniture. And, you know, just a little thing for you. If you ever get some IKEA furniture and you lose the instructions that come with it, the instructions are like a book and it doesn't have any words in it, right? It's just all pictures. That's because IKEA is Swedish, and who reads Swedish, right? Nobody, well, except Swedish people. There's not very many of them. So they do everything by graphic. But the other thing that they do is they have a website, and you can go to their website and you just put in the name of the item, and it'll give you the instructions on how to put it together. So you don't even need those paper instructions. Pretty awesome. So what? Some problems are creative. Oh, that's interesting. Huh? Strategies, heuristics, and good practices exist to help during the creative effort. These are things previous generation problem solvers found useful. So the point there being that you should notice this, and actually this is a hint for students that, you know, you're writing computer programs and, you know, then you decide to copy your friends and hand that in as your work. You know, it's going to be obvious. And the reason is because it's a creative process. When you write a computer program, usually there's 4 or 5 ways at least of solving the same problem, right? And so why would everybody in the class choose the same way, right? I mean, that'd be kind of weird, right? Or at least they'd have different variable names and different names for their modules and stuff. So yeah, there's a creative process in there. Actually, computing is not just scientific. It's scientific and artistic as well, I guess you could say. That you have to be a little bit creative about how you do it. So George Polya, Hungarian mathematician, how to solve it. The book takes the approach of problem solving. All right, so here we go. But this may be familiar to people who did science at high school. This is how we solve science problems. We form a hypothesis. So a hypothesis is going to be, I think that this happens because of this, something like that. Then you plan an experiment, and usually in science, you'll say, okay, what I'm going to do is I'm going to try and prove my hypothesis is wrong. That's what we actually do in science. It sounds kind of weird, but that's what we kind of do, right? This is what I think is going to happen. What can I do to prove that I'm wrong, that my hypothesis is wrong? So I'll try this experiment to see if it proves my hypothesis is wrong. If the experiment does not prove my hypothesis wrong, then I can proceed a bit further, I suppose. Execute the experiment, evaluate the results, come up with some kind of conclusion. So what Polya said is, well, maybe we could apply that to writing computer programs and solving problems with computers. Understand the problem is kind of like forming the hypothesis, which is, you know, this is what I think is happening. Devise a plan to solve the problem, execute the plan, and then review and extend. So the idea there of the review and extend is we kind of never ever finished with computers solving problems, because we always have to go back and check. Did we solve that in the best way? Have conditions changed? Do we have a new problem to solve? Have we created a new problem with the solution that we came up with before? As it says, getting started is hard. What is it? The 1,000-mile journey starts with the first step. So that's why the first step is really just to look at it and try and understand it in the simplest way that you can. And then you can start breaking it down into smaller bits. Don't go and start making a solution straight away. As soon as you sort of sit down, take your time to make sure that you've used the time to digest and understand that completely. So the first thing is defining the problem, and some would say it's the hardest thing. So as it says there, when we have a problem, what we have is we have a state which is undesirable, and we want to move to a desirable state. So whatever your problem is, I suppose the simplest problem you can think of in that way is I am hungry. That's an undesirable state. The desired state is to not be hungry anymore. So what will I do? All right. So for us, this is very easy. We go to the cafeteria, right? For 2,000 years ago, 10,000 years ago, our ancestors, that was a lot harder. Some of them spent all day solving that problem, right? I'm hungry. Oh, what now? I'm going to have to go hunting or grow something, right? But yeah, so it's a lot easier for us on that. You might find things undesirable that you need to move. As I said, it's undesirable to be hungry, but there's other things that are undesirable. Maybe there's processes that are frustrating. Maybe our customers are being not well treated by the systems. Maybe we're losing customers. Maybe our engineering processes are not efficient. There's lots of undesirable situations that you could think of. Maybe we can't keep track of our finances, whatever. Each of those is undesirable that could be solved by some solving a problem by computational thinking and then applying it with a computer, or not. Maybe applying it with not a computer solution. So don't try and answer a question that you don't understand. So try restating it in your own words. Try and use, so this representing a problem using pictures and diagrams, that's exactly abstraction, isn't it? Abstraction is making it as simple as you can. Use symbols, use diagrams. That is abstraction. There's some things that you won't know at the start, and so you should be prepared to adjust your definition of the problem as you go. All right, whatever the problem, key thing to remember is the goal defines what needs to be done and how it should be done. Not how it should be done, not how it should be done. Yeah, that's obvious. So how it should be done, that's the algorithm. And the goal is just going to tell you, okay, so this is our problem. Then we decide maybe multiple things that we can do to solve it. In the end, we'll come up with an algorithm. How do we know when the problem is solved? That would be a good way of defining the problem. So I'll know that I have solved this problem when this happens. Then that's a way of defining the problem. So here we got an example. So we got to plan a conference. The goal is going to be, okay, so you have to have 1 minute to think and define the goals of the conference. You guys all right for that, or are you getting too tired? You're going to have a conference and people are going to come and talk and they're going to eat, and because you've got to do that at conferences, right? Because you keep them there all day. So you're going to give them something to eat. They're going to have a lot of people together. They're going to have special guests who are experts, who are going to sort of drive the discussions, etc., like that. What would be the goal of the conference? Say let's say this is a conference on some computer engineering topic. What would be the goal, do you think? Too tired? Could be. All right, so you could have a conference on how to write programs, I suppose. Generally, yeah, all right, let's start with there. Let's see what we come up with here. So I mentioned to you, if you're going to have a conference, you're going to have to feed people. Notice what we're saying here is we're going to worry about that later, right? When we're defining the problem and coming up with our first solutions, we can, now why would we not worry about the dinner or the snack at the start? I would say because there's many different ways you can feed people. And also it's not a thing which it needs too much planning. I mean, you can just get on the phone and in a half hour, somebody will bring some food, right? Worst comes to worst. It's nice if it's better planned, but it can be done. There's other things that need to be planned a lot more early in the, you know what I mean? So how many chairs, stage the audience? Now you're not going to be able to do that until you know how many people are coming, right? So we can always do that later. The topic, would that be a place to start? Absolutely. All the things are going to flow from that. So now we're seeing a bit of an idea of how we sort of do this. We're defining the problem there with the topic of the conference. Then everything else can come later. Like these things, right? How many chairs? As I said, you could just about do that the day before the conference. Come up with that seating chart for the guest speakers. Yeah, I think that's not at the start. Yeah, you could do that a bit later. You've got to know who the guest speakers are first, right? Which company will do the advertisement? Yeah, I think that's later. Possible list of guest speakers. I think that might be a thing that we would start with at the start. So we got the topic. We would need to know the topic before we can get the list of guest speakers. But once we've got the topic, then we'd want to know the guest speakers and how we could go from there, right? If the end goal is more complicated, we should start on it earlier, right? Those are the things that were over on the left. If the things are less complicated and can be arranged quickly, we can look at them a bit later. They're not something that we need to start with. Always write your problems down, your problem and goals down. That way you can check later and make sure that what you're doing in your solution is actually applying to the problem. Oh, look at that. Oh, I was going to say, this thing goes on a lot longer than I thought. Sorry about this. All right, so here's a problem. And this is a problem where we're using decomposition to help us to solve the problem. So we got a police officer, we've got a crime, and we've got a bunch of clues. And so there's a crime that was committed. What kind of things would the police officer need to consider that you can see in that diagram that would help them? Yeah, they want to know what time. They'd want to know the nature of the crime. They probably want to talk to that witness. Anything else? Yeah, right. There's shoe size, right? They could probably measure that because different people have different shoes. And look, this officer is familiar with the fact that, like yesterday, there was another jewelry store that was broken into, and they know who did it, right? So it could be something like that. So very good answers that we gave, which was what was the crime, when was it committed, where was it committed, what evidence was there any witnesses, and have we seen, like, so that's straight up pattern recognition, isn't it? Similarities, but the other stuff is our decomposition and etc. Okay, here's another decomposition test. They want to make a chicken sandwich. Oh yeah, you like it with mayonnaise or no? I don't know. Chicken sandwich. It's sandwich, isn't it? It's not sandwich. But if you go to Australia, that's what they say. They say sandwich. Or actually, no, that's what they say. Actually, a lot of Australians say sanger. A sandwich. Sanger. I have a sanger. I don't know. They have baby talk in Australia. I don't know yet. 30-year-old people that use baby talk. I know, because I used to. I still do sometimes, right? All right. So what are you going to do if you're going to make this sanger or sandwich? Yeah. All right. Yeah. So one of the ingredients it mentions there is, well, do you like butter, or do you like what bread do you want? I mean, these are the questions that they ask you when you go to what's that sandwich place? Subway. If you ever eat a Subway sandwich, that's the first thing. Right? What bread do you want? You know, do you want? Yeah, and then you build it up, right? You want to cut it out. Okay, so I think you get the idea. And hallelujah, alhamdulillah, we came to the end of that. So that was a lot, and you guys were very good and patient, and hardly anybody went to sleep. So I appreciate that. Though you might want to stretch your legs now. It's been like 40 minutes. And then we can come back and we'll talk about the lab or something. Does that sound good? Yeah, so we're done on lecturing. Thanks for that, folks. Oh, unless there's any questions. Nobody dares ask a question now. I guess the rest of everybody's waiting to leave. Okay, please stand up, go outside.